Hey class, we're going to continue on with our notes for 3.2, which we were discussing the mean value theorem and Rolle's theorem. And I think we left off on example 3. This one I've already got worked out just to save some time for this video. So we're going to find the equation of a tangent line. So we've done this many times. So to find an equation of a tangent line, we need a slope and then we need a point. So it involves finding the derivative of your given function, and then also plugging in the point at which we're going to be finding that tangent line so that we can find the slope at that point. And then we have the point itself, which, we need the slope and the point. We've got our equation. Now, it says, but where are we doing this tangent line? It says, find the equation of the tangent line to the graph of our given function here. Now, in our interval from 0 to pi at the point which is the solution to the mean value theorem. So we are using the mean value theorem here. So what we want to do, remember, is we are going to, in our function, plug in these endpoints, and then we're going to find the slope of the line segment that connects those endpoints. So we're going to find like our average slope in there. And then we're going to do our derivative and set that equal to that slope so that we can find where does the instantaneous rate of change match that average rate of change. Okay, so starting off, we should note that, we'd maybe graph it, but it's a trig function. So this is going to be continuous. It's going to be differentiable. There's nothing, weird or funky about a trig function, a sine, function like this. It's just it's gonna be nice and smooth on that interval. Okay, so what we want to do is we want to find the y-coordinates of the endpoints, right? So f of 1 is 0, and f of pi is going to be 2 pi plus 1. Sorry, that isn't very clear. 2 pi plus 1. When I just plug those values into the function, you can probably easily see those y-coordinates, how they come out. And then when I do the derivative of this function, I'm going to get 2 plus cosine x. Now, what I did with these endpoints, remember, is we do the slope. So y-coordinate minus y-coordinate, x-coordinate minus x-coordinate. And when I simplify that, so I have 2 pi plus 1 minus 1 is the difference of the y-coordinates, and then 0, or pi minus 0 on the bottom. And so as this simplifies out, the 1s would cancel. 2 pi over pi ends up just being 2. Okay, so that is the slope of the secant line, we'd say, but it's the average rate of change, or it's the slope that connects these endpoints. Okay, now what we want to do is find that instantaneous rate of change that matches this slope of 2. So we're going to take our derivative, set it equal to 2. That's what we're doing here, and then we solve that equation to figure out the x-coordinate where we would have that slope of 2. Okay, so subtracting 2 from 2, we get cosine of x equals 0. And the solution to that, if you recall, at 90 degrees or pi over 2, that has a cosine value of 0. That's the one that falls in our interval. Okay, so x equals pi over 2, or c equals pi over 2. Okay, so we've got that. And then we also need to get the y-coordinate for that input. So back into our original function, we're going to do f of pi over 2. And simplifying that expression, we end up getting pi plus 2 for that. Okay, so we've got our point, our ordered pair, which is pi over 2, and then pi plus 2. That's our x and y coordinates. So those go here. Pi over 2, you've got x minus x, and then y minus y, which I moved over here. So this is your x plus 2, and then our slope is 2. So there's our equation of our tangent line. Okay, example 4, they're telling us that the mean value theorem does not apply. So we have to explain precisely why we cannot apply the mean value theorem to either of the two functions below. Looks like we have 3 of them actually here, so any of the 3 here on the provided intervals. Okay, so first of all, red flag is going to be we've got an absolute value function, because we know absolute value functions have sharp corners in them. We want to just make sure that that piece, the sharp corner itself, is going to fall in this interval. Now in this case, because it's x minus 3, it's going to be at 3 is where that x coordinate of 3 is in that interval. Okay, so what we would say here is f of x, a sharp corner means not differentiable. Okay, so f of x is not differentiable and sometimes to say not differentiable is probably enough, but we can be specific here and say there's a sharp corner at x equals 3. And maybe we want to say which is in the interval 2, 5. I guess that's probably clear on its own. We probably didn't have to say that, but just to be as clear as possible here, why we're explaining precisely why that doesn't apply. Not differentiable in the closed interval, or I guess they say technically, I guess it's in the open interval. So I really don't think that's going to be something that's going to get fussy on the AP graders. I don't think are going to get too fussy, but I guess in that open interval, I guess if you say the closed interval, it's also in the open interval, but it's not differentiable at that x equals 3. Okay, so then for part B, again, another red flag when we're looking at both continuity and differentiability. Continuity red flag is that you have a rational function, and we know that we're going to have an asymptote, which is that's a discontinuity, and does it occur in this interval between -3 and +1? Well, I can see that it occurs at -2, because when I put a -2 in there, I'm going to be dividing by 0. That's undefined. We get our vertical asymptote, and -2 does fall in this interval. Okay, so we're going to say f of x is not continuous. And we have to say specifically at x equals -2, which is in our closed interval -3 to 1. Okay, and this last one, okay, so this one might not be as clear, but if you have these rational exponents, if we were to take, so we're looking at differentiability here. This one's continuous. If you take a look at it on your calculator, you get a graph that looks kind of like this. And technically, actually, what's happening is we have a vertical tangent line right there at 0. Now, the way we could, if you're not sure, if like, well, it doesn't seem to be a problem with continuity, what about maybe just find its derivative and then take a look at it. So if I were to do the derivative, I'd have, what, 2/3 x to the -1/3. Well, with that x to the -1/3, then that means that we've got 2/3 on top, or I could do just the 2 on top, and then 3x to the 1/3 on the bottom. Well, that opens the opportunity for a vertical asymptote. So when x is 0, there's a vertical asymptote there. So there's a discontinuity at 0. 0 does fall in this interval. Okay, so we would say here h of x is not differentiable at x equals 0. So what I mean here is because this is the derivative, and there's that means that there's a place where the derivative is undefined, so it's not differentiable at x equals 0 because the derivative is undefined there. And really, with that in this graph, the way we see that is a vertical tangent line on the graph, because slope of a vertical line is undefined, right? And that's what we're seeing here. Okay, so we're going to say that h of x is not differentiable at x equals 0. So it's either going to be not continuous or not differentiable. Okay, and that's clearly in the interval, so stating where it happens. Okay, and then the last one, and there was a lot of writing for this, but let's talk through this one. So it says 2 stationary police cars are equipped with radar 5 miles apart on a highway as seen in the figure. Okay, so we've got, this is an expanded view and not really to scale, but okay, so as a semi-truck passes the first patrol car, its speed is clocked to 55 miles per hour. So he's good, he didn't get a speeding ticket there. Well, I assume that's not speeding on this highway. 4 minutes later, when the truck passes a second patrol car, its speed is clocked at 50 miles per hour. So again, he seems like he's probably okay. Prove that the truck did or did not exceed the 55 mile per hour speed limit at some time between the 2 police cars. Okay, well, seemingly he's doing all right. So the speed limit's 55. He's going 55, passing the one police car, then 50, passing the other one. But it does say that 4 minutes. Okay, so here's some key information. So in 4 minutes, he traveled 5 miles. Okay, so if we have that information, we can determine his average speed. Okay, and now when I say that average speed, I want to just jump back to what we've been talking about. Average. Here's average speed. Just randomly on a just generically on this graph, an average rate of change, right? It's the slope of we call it a secant line. Now, somewhere in there, there's an instantaneous rate of change that matches that, okay? So let's keep that in mind. Let's find the average rate of change. We know that he's going slow at the endpoints, right? We're at the beginning and at the end of when he was clocked with his speed. But what happened in the middle? Well, to determine that, let's find the average rate of change. Okay, so if you recall, to find speed, there's distance equals rate times time, right? Which means that rate equals distance divided by time. So we have those two things. We have a distance of 5 miles, we have a time of 4 minutes. Now we probably want to look at miles per hour. Right now we've got miles in minutes, but 4 minutes would be 4/60ths of an hour, right? So I'm going to take that 5 miles and divide it by 4/60ths. Now this would be, you could do this on your calculator, 5 divided by 4/60ths, whatever that decimal is. What you find is that turns out to be 75, and that would be miles per hour then if I convert this 4 minutes into a 4/60ths of an hour. Okay, so what does that tell us? Okay, well, if his average speed in that interval is 75, he clearly has to have been speeding somewhere between, where the first police car, second police car clocked him at these slower speeds, and he really stepped it down in between there. So he was going slow when he saw the first one. He sped up by a lot. Had to be going faster actually than 75. But so here's the way I'm going to say this. So the semi traveled 5 miles in 4 minutes. So his average speed was found by dividing 5 miles divided by 4 minutes, or 4/60ths of an hour. Comes out at 75 miles per hour. So this problem can be modeled by a continuous and differentiable function. Okay, so just it's a constant, continuous function, I should say, where speed is changing throughout the time interval from 0 to 4 minutes, but it's continuous, so that's why we can model it with a differentiable continuous function. So the mean value theorem would apply in this case. Since its average rate of change is 75 miles per hour in the time interval from 0 to 4 minutes, then the mean value theorem guarantees that his instantaneous rate of change was equal to 75 miles per hour at least once in that time interval. And that's exactly what the mean value theorem states. It says, well, whatever that average rate of change is, there has to be at least one spot in there with the instantaneous, so at one point in time he was going at least 75 miles per hour. Okay, and so that's what we're kind of applying it to a real life situation there. Okay, so that is all for 3.2 notes.